Hello, in this lecture we're going to begin our discussion of basic concepts of biomedical instrumentation. This is chapter 1, or concepts from chapter 1 that are from the book by uh, Webster, Medical Instrumentation, Application, and Design, the 4th edition. What you see here is an overall block diagram that just shows a generalized instrumentation system. And what we have are various components, starting with the measure end, which is what you're actually measuring. Now, sometimes you use some sort of stimulation. For example, if you're taking an X-ray, you wouldn't just have the human body, you would have the radiation that interacts with the human body. So sometimes there is an input into what's being measured. And then once you've identified what's being measured, oftentimes there's also a calibration signal. You now have your sensor, and so within your sensor you typically have a primary sensing element. That can be, it's usually something physical like an electrode placed on the skin, or a thermocouple placed on the skin, or even a wireless type device that's picking up some kind of signal from the body. And then you have a conversion element, and that is usually often contained within the sensor. So for example, sometimes the sensor itself provides the conversion. You may be measuring temperature and the sensor may output a voltage. Other times you'll have an additional element that goes within the sensor that gives you this conversion to a quantity that you can work with. From there is some signal processing that has to be done. This is often the use of an amplifier. Sometimes it's the use of various filters to get rid of noise or other components that you don't want in your signal, or any number of other things that can be present in your signal processing. And then from that point, once the signal is processed, it's sent to an output display. And that's got to be some kind of perceptible output. Typically, this is a computer screen, but if you have a handheld device, like some of the new temperature sensors, it can actually be a LED readout on the device itself. In the old school, we actually printed out strip chart recordings of heart rates and EEGs, and sometimes that is still useful in the field. Intermediate steps, sometimes before the signal processing, you'll have a data storage. That's because a lot of times you don't do your signal processing in line. You may do your signal processing after the fact, or it could work the other way. The signal processing can occur, and then the signal can go into data storage. Also, sometimes you're transmitting data. As we get more and more into remote healthcare, that's going to become a bigger deal. And how to actually process the data so that it can transmit easily becomes a big deal. In the first few chapters of this book, we'll go through each of these elements briefly. And you must keep in mind that each of these elements within an instrumentation system could itself form an entire course. So this course, as we look at instrumentation systems, is primarily going to be an overview or a survey course where we hit the highlights of different areas. In the latter chapters of the book, we're going to go back and look specifically at different types of things that we're going to measure and categorize the remaining material in the course that way. So, talking about some terminology that was shown on the previous figure, the measurand is the property, quantity, or condition that's being measured, and these fall into different categories. They can include biopotentials, pressure, flow, dimensions, displacement, impedance, temperature, and even chemical concentrations. The sensor is a transducer that converts one form of energy to another. So specifically in our case, we're converting to electrical energy. Signal conditioning is a part of the instrumentation that converts the signal to another form, or conditions the signal rather. So this can be from analog to digital. It can include signal filters, it can include amplifiers, it can do impedance matching between your display and your recording device, and various other components that go into this signal conditioning. This doesn't change the type of signal from, say, thermal to electrical, but it changes an electrical signal in one form to another form. So maybe it filters out noise, or maybe it digitizes an analog signal. And then finally, the output display is the part of the system that displays or stores information for the user. So there are different modalities of measuring, and we can sort of compare and contrast these. There are direct versus indirect. So, for example, X-rays will give an indirect measure of the state of the organs. You're not actually touching or viewing the organs. You're using a radiative method to look at input and output of that radiation and determine what's in between. Sampling versus continuous. Um, Things like body temperature or other variables that change very slowly can be sampled infrequently. It may be fine to do a body temperature measure every 20 minutes, every 30 minutes, whereas things like your heart rate may need a continuous observation. So this is not sampling and continuous in the digital and analog sense. It's sampling and continuous in the sort of overview of the measurement sense. Do you need continuous data, or is it okay to sample every once in a while? Generating versus modulating sensors. So modulating sensors will need an additional power that's supplied to them by some external energy source. And then real-time versus delayed modes, we touched on this a little bit. In some cases, the signal will acquire the system, or the sensor will acquire the signal and the system displays it in real time. In other cases, you acquire the signal and then there's some delay between the acquisition and the display. Some systems work both ways. A classic example of this would be the MRI. When you have an MRI done, the MRI technician is actually getting a real-time display of your MRI, but the radiologist and the person who reads that MRI actually views it after the fact, after some processing has been done. So measurement constraints are significant, and there are a number of these depending on what you're actually measuring. So just thinking about some practical things, some of the constraints that you would have in a system. Sometimes the parameter range of the variable might be too large. It could be that the movement is too great, the variation of temperature is too great, and that's not matched to the capabilities of the sensor. And so if you exceed the operating range of your sensor, particularly if the sensor has both a linear and a nonlinear range, then you go into an area where the instrument may not be calibrated. Another limitation would be that the variable that you're measuring is not accessible. So these would tend to be more internal variables that where you can't actually make a good direct measurement. Interference from other nearby systems. This is actually very common in a lot of environments. You may have been in hospitals yourself or with relatives and seen in certain areas there are no cell phone signs. It was thought at one time that cell phones interfered with instrumentation. People are kind of backing off that a little bit, but there are all sorts of interference present. Even if you're measuring something, for example, if you're taking measurement of a sound, just the ambient noise in the room, ambient electrical noise from power lines, any number of things can interfere with your measurement, and that usually is a constraint. Non-deterministic variables or inherent variability. So in that case, that would be just the statistical nature of what you're measuring. Most things in the body, most signals in the body are measured as being stochastic or statistically driven processes. Potential to damage of biological tissue by measurement devices or radiation. So every measurement that you make has an inherent risk, or most measurements have an inherent risk. There are very few passive measurements, especially anything that is invasive to the body contains certainly a potential for damage, and that would include radiation. And then finally, the desire to minimize electric shock will sometimes introduce a constraint onto the system. Now, there are lots of different ways to categorize measurements. One way to categorize is by the quantity being measured. Are you measuring the flow or pressure, electrical activity in the cell? Another is to categorize measurements by the principle of transduction. So are you using capacitive probes? There are any number of physical quantities that can be measured using capacitive probes. You can characterize measurements by the organ system, so the cardiovascular system, the neurological system. Or you can categorize measurements by their medical specialty, so by their clinical specialty, so OBGYN, cardiology, measurements that fall within those groups. Sometimes companies are organized around clinical medical specialties as opposed to something like principles of transduction when they're selling end products, but suppliers of sensors might be more organized around principles of transduction. So some of this is sort of an interplay between commercial aspects of measurements and the physics of the measurement. So here is a table that just presents excuse me, just presents a number of different medical and physiological parameters and how they're measured. So you can look at any number of these. We'll look at electrocardiography because that's one of the things that I'm familiar with and have measured in my lab before. So the ECG basically measures the heart rate, the heartbeat signal. The principal measurement range of parameters. So typically the output of the probe or the electrode that measures the ECG is between 0.5 and 4 millivolts. And the frequency range that's present within an EEG signal tends to be from 0.1 to 250 hertz. And the actual sensor that's used would be skin electrodes. Now you can see there are a number of others that are given. Some interesting ones might be respiratory rate. People tend to breathe between 2 and 50 breaths per minute. I've actually seen babies and young children who are sick breathe much faster than that. Your signal frequency range is from 0.1 to 10 hertz, and this can be measured with a strain gauge on the chest. You can measure impedance. You can measure using a nasal thermistor. This is one of the things that people are trying to develop wireless measurements for, so that they can do things like monitor respiration rates in environments where you can't necessarily tend to every patient and put a sensor on every person. So, for example, in the military field or battlefield or in the emergency room environment or post-traumatic episode of some sort, post-natural disaster, post-traumatic event where you can't necessarily keep a monitor on everyone, but you may be able to have a wireless system that monitors breathing to make sure that people who you haven't yet gotten to are still breathing. So those are just some various types of measurements. Here's an illustration of interfering and modifying inputs and what's meant by that. So your desired inputs basically are the measurand. So what are you trying to measure? So in this particular case, the desired input that we're trying to measure is the heartbeat. And so we have a couple of electrodes here on the body, and then they come to a differential amplifier. We're measuring some displacement currents are present because we have some external voltages in the room. There are some magnetic fields due to 60 hertz. So from the body, from the cabling that goes from the body to the differential amplifier, to the signals in the room and the capacitive coupling between various cables in the room, all of that is going into the differential amplifier. So not only is your measurand being, your desired input being measured, but other things too. So interfering inputs would be quantities that affect the instrument due to how the desired input is acquired and measured. So an example of that would be the 60 hertz noise in the room and the capacitive coupling. So that would be something that you really couldn't control because they're present in the environment. You can do some shielding to try to minimize those, and we'll talk about that toward the end of the course, how to do as effective grounding and shielding as you can, but you can't really eliminate them. The modifying inputs are the inputs that affect the instrument itself. So, for example, how you place the cables on the patient. And you may not know, but acquiring an EKG or ECG is really important. How the cables are placed, if they're not placed quite right, the way the voltage is picked up is changed, and so you can get things that look abnormal that may not actually be abnormal. The impedance between the electrode and the skin is another modifying input. If you have a high impedance or if the electrode is slipping around, it's going to introduce what appears to be noise On the other hand, if you have a very good contact, then you get a good representation of what your signal actually is. Negative feedback is actually something that's used to minimize the impact of modifying inputs, and it makes the output less dependent on the transfer function of the input. So basically, your output y, instead of being directly related to your input x, or instead of being related by this factor g sub d, which would be sort of a transfer function that incorporates everything that's in your measurement system, the use of negative feedback changes that so that y is equal to x times this quotient, where this h of f is present in a feedback loop. And what that does is that takes this from being something that's very dependent on the value of g sub d to something that's not so dependent on the value of g sub d. And what that tends to do is that tends to then stabilize your system response so you can have external inputs that are modified or minimized in the feedback loop. So that concludes this portion of the lecture on materials in Module 1.